There's just one more problem I want to show you in this unit. And it's because in the regular section of Physics 113, this is a homework problem. And I think it's worth seeing because it really combines kind of all of the ideas that we've been looking at so far. So we start out with an inclined plane, just like we saw earlier. It makes some angle theta. And we have a block resting on top. Okay? Now we're going to say that there's no friction. Okay? And we want the block to not slide down the hill. So we don't want the block to slide. And the way we're going to prevent that from happening is we're going to apply a force F to the incline. Okay? So now we're going to have two masses. We're going to call the mass of the incline mass 1 and the mass of the block mass 2. So the whole system is going to have a net acceleration to the right. We're going to assume that the incline is also on a frictionless surface. So there's no friction at all involved in this problem. And what we want to do is we want to find out what force F we have to apply to make it so that mass 2 doesn't slide down. Okay? So there's one kind of important trick to a problem like this. And until you've solved enough of these problems, you might not recognize what it is. But this is going to be one of those times where I'm going to ask you to pause it in a second. But I'm going to give you a hint, okay? The hint is, remember that when we had just a regular inclined plane, okay, that in that case, we changed our x and y direct axis. So our x was in the direction down the plane and our y was normal to the plane. And we did that because we wanted to make this into a one-dimensional motion problem. Okay? So now we want to do the same thing for this problem. We want to split it up so that we have only one direction. We can actually write this problem as a one-dimensional motion problem. So I want you to pause the video right now, and I want you to think about where you would draw your x and y axes and what your x direction and y direction should be, so that this becomes a one-dimensional problem. So pause it right now and think about that. Okay. So we know that the force is applying to the right, which means the entire system is going to be moving to the right. And we know we don't want the block to slide down the ramp, but that's the same as saying we don't want its vertical position to change. So in other words, in this case, we're actually just going to use the regular x-y axis. And if we do that, this ends up still becoming a one-dimensional problem. So you can see the reason that I'm showing this example now, because it's important to realize when you're setting up a problem, what's the easiest reference frame to use to make your dynamics as simple as possible. And in this case, surprisingly, it's actually just to keep the regular xy axis. Okay, so now if we do this, we can draw our forces on the objects. So we have a force of gravity pushing down on the plane and a normal force pushing against it. We have a force of gravity pushing down on mass 2, and we have a normal force. This is really the force from 1, 2 pushing up on it. But that means we also have a force F21 pushing back on the plane. Okay? And now we want to get our angle straight. So again, if we look at our gravitational force, we know that this angle is 90 minus theta. So this angle is going to be theta. Okay? If we look at our normal force then, again, we can see that this angle is 90 minus theta, which means this opposite angle is also 90 minus theta. We'll do this, well, actually, we'll do this. So this angle is 90 minus theta, which means this angle here is theta. Okay, so in other words, if we draw this here, we have this angle is theta. Okay, so make sure you understand that we've done a lot of work with vectors and with trigonometry before, but again, it's important to make sure we get our angles right, because that's going to be the easiest way that we can mess up this problem. All right, so now if we look at the plane or the wedge, we see that the net force is going to be equal to F in the x direction, a minus m1g in the y direction, a normal force on 1 in the y direction, and now we have this force pushing back on us, and so we need to find the proper angle for this one. So we'll look at this down here again. So this is the plane. We have our gravitational force mg. Okay, we have F12, or sorry, well, F21 in this case. Okay, so again, we know that this angle is theta. Okay, so the angle F21 in the y direction then is going to be the y component of this, right? So this is going to be in the x direction minus F21, and it's going to be mg cosine mg sine theta, and in the y direction minus F21 cosine theta, and this is equal to m1a in the x direction. Okay, now we'll look at the block, and for the block we see that F net is going to be equal to a 0, a minus m1g in the y direction, and then the only other force on it is this normal force, so F12 in the x direction now. So we see, so we have F12 and the x component. I did this angle wrong. This angle is not theta. This angle is not theta. This angle is theta. This angle is not theta, so this angle is theta. So this should be F12 sine theta, and this should be F12 cosine theta. So if you noticed that earlier, you were right that I did switch those angles. This is not theta. This angle is theta, because we have theta, we have 90 minus theta, which means this angle is theta, which means this is 90 minus theta, which means this is theta. Okay, and all of this is going to be equal to m2, a in the x direction, 0 in the y direction. Okay, so now we can look at the y component here, and we can see that that F12 cosine theta is equal to m1g. So this tells us that F12 is equal to m1g divided by the cosine of theta. And then we can go back, and now we plug that into the first part of the equation here, the x components. And so we see that this is equal to A is F12 over m2 sine theta, which is just equal to, oops, did I write m? That should have been an m2g. So the m's cancel out, and so we are just left with a, because this is an m2 now, okay, so we're just left with a g tangent of theta. Okay, so that's the acceleration of the system. So now we go back up to our first equation here, and so we see that m1a is equal to F minus F12 sine theta, which is equal to f minus m2g over cosine theta times sine theta, which is tan theta. Okay, so now we can move this term over to the other side. We can plug in a. So we see that m1 plus m2 times g tangent of theta is equal to f. And here's our answer to the problem. Okay, so we solve this just like we solved the other problems. Notice that I made a few mistakes along the way that I caught just because I know I've worked this problem before, and I know basically what the answer should look like. But you can see that there's a lot of places to make mistakes, right? It's very easy to swap an angle. It's very easy to have a mass that we confuse the mass 1 and mass 2. Some of the mistakes that I made and caught along the way. But then you get to the final answer here, and again we see that this makes sense, right? It's the total force is the sum of the mass. Looking at the intuitive method, we know that it's going to be the sum of the masses times their acceleration. And then we just need to find the acceleration, and we see that working through the whole framework, we got to the acceleration is g times tangent of theta. And so this is really kind of the most difficult problem that you would see in this class. And so I would look at it, I'd make sure you understand it, and that you could work problems of this difficulty. Not necessarily for your unit exams, but for something like the MCAT, or a final in this course, or something like that. Okay.